recording. All right, so over here we are going to go to your portal just to pick up to take a look at the this week's material. Next week, if you are not, if you're still working on array lists, that's okay, but I would really suggest, and not to you, portal, I need Canvas. I would really suggest that you try to make sure that you're ready to start on linked lists on Monday. Not this Monday, but next Monday. Because linked lists is where we start getting is basically our hurdle in the class. The good news is that if you can handle linked lists and you can take care of the linked lists, you're not going to have any trouble for the rest of the semester. You're probably going to end up with a B or higher. It's students who struggle with the linked list portion of the class that end up having to fight for this to get the C or B. If you're having trouble with if you don't have trouble with linked lists, or rather if you feel, you're going to have trouble to begin with. Okay, don't get me wrong. But if you get a handle on it in time for the first exam, yeah, you're probably going to make a B and maybe B or A. So, so also for the linked list, you'll notice that that's weird. Why do you have 2 assignments? Are you crazy, Professor Rosen? No, that is, if you click over here, you'll note that there are 2 assignments, and you get to choose which one you want to do. The first one is easier, the Josephus problem. The second one, solitary encryption, is more difficult, but you get 20 extra credit points for completing it. Both of them use the same base code, so if you find that, I started solitary encryption, and it was a bit more than I could chew off at the moment because of all my other classes, it's very little effort to go switch to the Josephus problem because you're not going to really be throwing out that core code they both share. So let's see. I'll make sure. Hopefully, all these things. Do these all make sense? No, that due date does not make sense. Let's go and fix that due date. That due date does not make sense at all. Okay. Yeah, please, if you find due dates that don't make sense, please let me know. Okay? Because, again, the import process is sometimes a bit of a mess. Okay. Please let me know. All right. Yeah, you thought you were going to be working all night on that. Yeah. So no. We only just introduced the material. That means you've got a week to master it. So there you go. So, okay. Now that you've got that bit of relief, let's go and take a look at it in a very non-stressful manner, okay? So big O notation, you will be covered hopefully in more detail in 2166, right? So I have to teach enough of it so that you can use it in my class without making it feel like without spending time that you will spend in 2166 if you are a computer science major or a data science major. If you're IST, you don't have to take 2166, but you should learn about kind of the verbiage of big O notation because because most programmers know how to talk about big O notation. And the idea here is that we cannot really measure the efficiency of algorithms, by saying, it takes about 70 seconds to run on this computer because depending on what load that computer has, that time can vary, or what configuration my computer has versus the configuration your computer has. So what we do is that we say, okay, given this algorithm, as the input gets really large, what happens to the workload? So that's what, so T of n is the time, and we basically say, okay, if this takes T of n time, where n is our input size, it takes n to the third power plus n squared plus 10 to the 7th time units, whatever that unit is, second, millisecond, doesn't matter. Again, because n is like our input size. Okay. Basically, what we find is that once that input size becomes ridiculously large, like billions upon billions upon billions, this stops mattering. And this stops mattering. This completely dominates. So we say it's an O of n cubed algorithm. That given any input, the workload is about a cube of that. Okay. And so that's what that means. A lot of the algorithms we deal with in class are not going to be, and are going to be of a few cases, which I'll go over in a second. The other thing to consider is that constant factors don't matter. 500n and 1/5000th of an n, they're both O of n algorithms. They both have a linear relationship. If you graph it, it's going to be a straight line. Okay? What matters is the rate of growth. So again, over here, it doesn't matter. Notice over here that we just simply say that this 50n cubed becomes n cubed. And then for our algorithms that you're going to be doing in classes, counting the number of nested loops usually works with a few exceptions. Basically, if we're doing a count of the nested loops, where we have like an array or array list and we iterate over it once, that's O of n. But if we have a nested loop so for every item in this list, I have to go and check this item against every other item in the list, that's O of n squared. So that ends up being a bit of a mess. First, basically, this first exercise asks you to convert it according to those rules. It's weird, but the first two should be fairly straightforward. Okay, you have to use FOIL to figure out the second one, right? But it's number 3 and number 4 that I should draw your attention to if you have not taken Calculus 2, and should remind you of if you've taken Calculus 2. This third one is called the triangular number series. It is a very common pattern in computer science. A good example of this is that if you efficiently is the unique method for assignment 2. Assignment 2, first problem. The unique method asks, given each item, is every item unique? And the way you solve that is you check every item against every other item. If you did it efficiently, how would you have done that? I brought sorry, I'm looking for my stylus in my backpack, so there it is. Okay, so say you have 5, 7, 2, 4, 3, okay? And there's a total of n items, okay? There's a total of n items here. In the for the isUnique function, if you did it efficiently, what you'll do is you'll start at 5, and you'll check 5 against 7, and then against 2, and then against 4, and then 3, and all the others, and you're gonna do a total of n minus 1 comparisons, okay? And then if you do, so you've checked it, it's fine, all unique still. Then you go to 7, and then you check 7 against not all the other ones, but all the ones to the right of it. You don't need to check 7 against 5 because you checked 5 against 7, right? So in that case, I'll check 7 against 2, 4, 3, So total of n minus 2 rather than another n minus 1 checks. So you can be efficient like that. And then I'll check 2 against 4, right? And 3, and then 4 against 3, n minus 4. And see how we kind of got a little triangle going there and the number of dots I've done? And basically, if we continue on this pattern, we'll get like 3 checks, then 2 checks, then 1 check, right? And so if we add up all the number of checks, that would be n minus 1 plus n minus 2, probably should parenthesize those, to 3 plus 2 plus 1 is equal to something, right? And let's go ahead and flip that around, right? 1 plus 2 plus 3, n minus 1, sorry, not the n minus 1, but the n minus 2 plus n minus 1. So as you can see, that's very simple. This is almost identically the same as this, only it goes up to n minus 1 instead of n. But I mean, that's just simply choosing an end point, right? An end point. So what does that equal to? Well, as I mentioned, this pattern is called the triangular number series. That means, and if the series has a title, that means it has a Wikipedia article. So let's go there. Triangular number series. Okay? So, for those of you in Calc 2, this should not be scary math. For those of you who are not taking Calc 2, this should be moderately scary. But what that simply says is that, hey, here's the numbers from 1 to n all added together. Right? That looks familiar. That's what I have in my homework. And then it gives you a nice formula over here as to what that converges to. This series converges to something. N times n minus n plus 1 over 2. And we see that, and we can kind of see that. Like if we were to extend this out and draw a square around it, those dots kind of make up half the square. So we're going to do a very formal proof of this via induction on Wednesday. I don't expect any of you have done induction before. If you have, great. You'll be able to easily follow along. But induction is a very good way to know how these things work. It will also give you an answer, almost certainly, on one of your homeworks in calculus, if you have to take that course, because they love using this one and the other series. So here we have n times n plus 1 over 2, which would be n squared plus n. So even though it looks like it's O of n, it's not, because of how it converges. That's the only two problems where you have to be aware of that. You can go ahead and look up the other one by, on Google by typing in 1 squared plus 2 squared plus 3 squares and see its convergence is very similar. Okay. These all ask you about like how long these operations take in array lists, which I go over in the videos. Okay. This one is from a puzzle book that I enjoyed as a kid. It is actually it is actually related to, it is actually a very interesting algorithmic puzzle or problem, an NP complete problem actually, as it turns out, which means it's basically as hard as some of our hardest problems that are in polynomial time. So that's pretty cool. And then it asks you, hey, how long would it take? So basically it asks, okay, look up this problem and see, and basically see how this is that problem. Okay. This one, BOGO sort. Again, it's got a name. So, and I've mentioned that this is used only for pedagogical purposes. The BOGO sort algorithm is a sorting algorithm that works like this. Suppose I have a deck of cards and I wanted to sort the deck of cards. I would sort it by throwing it up in the air, putting all the cards together, and then checking if they'd magically arrange themselves in the proper order. If I haven't done so, do it again. So while the algorithm is while not sorted, shuffle. Okay, very terrible algorithm. Worst case, asking you for the worst case runtime, like how, if you're really, and think about it in terms of if you're really freaking unlucky, how long would this take? And then statistically speaking, how long, in the average case is saying, statistically speaking, how long should it take? Think about a deck of cards. A deck of cards has 52 factorial permutations to it. How many of those permutations am I expected to go through before I stumble across the correct answer? Okay. And then finally, for problem 23, we refer back to lab 2, which is the problems you just wrote. Now, in this class, in our class, with data structures, we will be dealing with a grand total of, I think, 5 runtimes. To begin with, we're just going to be dealing with very basic runtimes. O of n squared, O of n, and constant time. Those are the ones we primarily use in this until we get to trees. Okay? So basically on your exam, one of the ways I test Big O is asking you what is the Big O runtime of what you just wrote. It isn't constant, so it's probably one of those two. You probably didn't write a constant algorithm. Or on the exam, I'll say, make sure that this algorithm takes linear time as opposed to quadratic time. And then there's a penalty if you don't do it for that. So regardless, what do these mean? Constant time means there's no relationship between the input size. This is an example. This is checking the size of the array. It doesn't matter how big the array is. You can just check the size variable and figure out how big it is. You don't have to go and manually count it. If you did manually have to count everything in the array, that takes O of n time. If you want to find something in an array, that takes O of n time. Having to go through once every item in an array or an array list takes O of n time. Okay? Copying takes O of n time. And another way to think of this, which will be very useful for the next one, is if we double the amount of work, double the size of the array, that means it's going to take twice as much work. If I add one more unit, right? If I add one more thing to O of n, to an O of n algorithm, if I add one more item size, it's going to take just a little bit more work, right? And if I change the size for a constant time algorithm, it's not going to change at all. Okay. For O of n squared, that means that basically that, here is the input size, and here's the amount of time it takes. And it just follows that parabolic path up. Okay. Now this seems terrible, but it's not nearly as terrible as other things, as we'll eventually see. But the idea here is that if I double the size of this, if I double the size of our input, it's gonna take 4 times as long. If I double it, it's gonna take 4 times as long. If I have 10 times as many items, it's gonna take 100 times as long. All right. And then if I add one item, let's look at our isUnique function. If I were to add one more item, I'd have n more checks to do, right? So adding one more item here just adds one more unit of work. Adding one more item for n squared takes n more work, right? A good way I like to think of it, as a professor who has to grade exams, is grading exams. Grading another student's exam, finally, that's fine. That's just one more exam. It's not going to take much work. Okay, I can predict how long that's going to take. But suppose I'm a really paranoid professor who's really paranoid about plagiarism and checking every exam against every other exam to make sure that there's not any, any kind of funny business going on. And I'm, again, very paranoid here. I wouldn't do that because what does that mean? Well, if I have one more exam to grade, I have to now take this exam and check it against every other exam, which is a whole lot more work for one extra exam. So that's an n squared algorithm. So adding one more item means a lot more work. Adding one more item means a little bit of work, relatively speaking. Okay, that's really the difference in the growth rates, right? Constant time doesn't change. Linear time, it's some kind of linear relationship. Okay, doesn't matter which kind of curve we're looking at. And again, quadratic means we've just kind of got this parabola. The other two we'll learn in this class later on is when we're going over recursion, we'll learn about log n time. The good news is that you will stop being afraid of logarithms because they're not scary. You've just been taught them wrong your entire life. It asks, how many times can we split something? That is what logarithms tell you. Forget that relationship between exponents and logarithms. That's not useful for programming. It's all about how many times can you split something. And similarly, we'll learn about when we're dealing with sorting, we'll be getting into n times log n time, or log linear time. If you can write a log linear algorithm on an interview question, that's probably a very good answer. Okay, that may be as good as you can get without having to use any extra space. That is the other thing I should mention. We've been talking about time complexity, but you can use this format to talk about the amount of space that would be used by an algorithm. Like, do you need extra space? Do you need to make a copy of the array? Do you need to make a square, n copies of the array? So depending on that, so if you because sometimes we care about space. And then also another thing that's useful if you're writing algorithms for these little guys, the amount of energy consumption of certain algorithms, because some algorithms require you to wake up more often. So we can use that for energy. But the reason we care about time is because time is always the most important. It is the most expensive because you can't buy it. If you need more energy, great, go buy another battery. You need more space, buy a new hard drive. You need another minute, can't buy that. Want another minute to spend with your grandmother, can't buy that. Go and call your grandmother, by the way. You cannot buy time. You cannot get extra time. Time is the most important because it is the most valuable. So again, that's why why we do our analysis in terms of time. You can't buy it. You can get faster at algorithms, but you can't buy more time. So again, the way you turn this in is write all of these. Okay? So I write all these down, come and demo it to me. That's great. Once you're done with this, feel free to move on to what is Module 4. And again, with Module 4, in case you missed that, you get to choose. That's not two different algorithms. Not two different assignments that you have to do. You only have to do one of them. More comfortable, less comfortable. This one takes about, the solitaire encryption, I would say, takes about twice as much work and gets you 20 extra credit points, which is a whole lot. I generally do drop an assignment, but this is not one of the ones we drop. Or is it? Kind of. Essentially, the way it will appear in your gradebook is that one of these will be dropped. The one you don't, you'll get a 0 on the one you don't do, and then that one will be dropped. So it's just the way I have to hack it in for that to work. So, but regardless, it is but again, choose whichever one you want to do for the linkless one. Okay? So, again, I need to go back and fix these deadlines to make sure that they make sense, but again, I've adjusted that from being due tomorrow to being due next week because that was not correct in the slightest. It does not make sense that this would be due before the other homework. If you see inconsistencies like this, please feel free to reach out. You're probably not the only one confused about that. It's more likely because it just doesn't make sense. All right, so I'm going to go around the room to make sure I've got plenty of time to talk with people. So.